Okay, so we're in section 3.5 now. Up until this point, we've been looking at a number of different terms and connectives, logical connectives, surrounding this idea of formal logic or symbolic logic. At this point, what we want to do is start looking at an application of logic, some of the stuff we've been studying towards analyzing arguments. This is kind of one of the major things that we want to do with logic, is take an argument, analyze it, determine whether an argument is valid or invalid. So we're going to start with a little bit of terminology. This is a relatively short section. We're going to lay down some terms, and then we're just going to run through several examples to give you an idea of how we approach analyzing arguments using something called Euler diagrams. So let's start with that. A logical argument is an argument that consists of what we call premises. Premises are assumptions, laws, rules, widely held ideas, or observations. And then those premises are followed by a conclusion. And we'll be able to see in the examples which parts of an argument make up the premises, which parts of the argument make up the conclusion. When we analyze an argument, what we're doing is we're using logic to determine whether the conclusion in that argument actually follows from the premises. And what we mean by that is if the premises of an argument are all assumed to be true, then the conclusion should also be true as a consequence of those premises if the argument is valid. Okay? And we're going to see that sometimes you can have arguments that are valid but are simultaneously ridiculous. But validity of an argument is just the fact that a conclusion would follow from your premises. So again, we call an argument valid if the conclusion is true whenever all of the premises are true. If that's not the case, if all of the premises are true in an argument, and that doesn't necessarily imply that the conclusion is also true, then we call that argument invalid, and we say that it's a fallacy. These are all terms that you're probably familiar with just from common language, but we have definitions associated with these that we are going to use in this section. So there's different ways of analyzing arguments, and in section 3.6 we'll look at how to use truth tables, the stuff we've been working with in chapter 3 up until this point, to analyze those arguments. But in this section we're going to focus on something called Euler diagrams. It looks like it says Euler, but that's named after a very famous, very prolific mathematician, Leonard Euler, and this is one of the things that we attribute to him. I'm going to use the examples to illustrate how this works. Now, Euler diagrams are very similar to Venn diagrams. They have kind of a similar meaning. We're drawing circles that can either intersect or contain each other or not intersect at all, kind of in a similar way that you would with a Venn diagram when we were talking about sets. However, they're not exactly the same as Venn diagrams. So when we're going to use Euler diagrams is when we're analyzing an argument that it contains quantifiers, existential or universal quantifiers. So let's take a look at this first example. This is the structure that we're typically going to see arguments represented in. You notice that we have a couple of sentences here. All blogs contain writing, and then this book contains writing. So these two sentences make up our premises for the argument. And then the last sentence that follows, or that's below this line right here, that's the conclusion. So the idea here is to take a look at these premises and try to determine if these premises are true. Is the conclusion true? Now, this is kind of an important part of analyzing these arguments. These premises don't have to be true in reality. So, for example, if you can find a book, or if not all blogs do contain writing, if that's something that's not actually true in reality, maybe somebody started a blog and never typed anything in it. So maybe there exists a blog out there somewhere that does not contain writing. Whether or not these premises hold up in reality, for the sake of analyzing an argument, we automatically assume that all of the premises are true. And that way, we're not worrying about trying to find evidence for these. We're just trying to see that if they are true, does this conclusion also hold true under that assumption? So another thing you're going to notice is this first sentence uses a universal quantifier, the word all, okay? And we're describing two things, blogs and things that contain writing. I'm going to represent those with circles in such a way that the universal quantifier is accounted for. So I'm going to do a larger circle, and I'm going to write in there things that contain writing. Okay? Now, if all blogs contain writing, and if this circle is, I'm thinking of this in the sense that I think of the circles in Venn diagrams. Think of this circle as the set of all things that contain writing. If all blogs contain writing, then all blogs should live inside this circle. There should be no blogs outside of this circle, because that would imply that there are blogs that do not contain writing, and we're going to assume that this premise is automatically true. So I'm going to create another circle representing all blogs, but the entire circle should live completely within the larger circle that I already drew. This is blogs, okay? When you're first learning about Euler diagrams, it can be difficult in a case like this to determine, which circle goes inside which. And so what you want to do, again, is think of these circles as like Venn diagrams or representative of sets. So see if there's anything that violates this premise. For example, if I made the outside circle blogs and the inside circle things that contain writing, then I could pick some element outside of this circle here, and that would represent a blog that does not belong in the circle of things that contain all writing. So that would be a blog that does not contain writing, violating this premise. Okay, so this is an Euler diagram representing this first premise. Now it says this book contains writing. So we're going to assume that that premise is true. What does that mean for this book that we're talking about? Well, notice we're identifying a single book. It's not a set of books. So this book does not get its own circle. We're going to represent that a different way. If this book contains writing, is it possible that this conclusion is false? That's the way I want to think about this. Or does the fact that this book contains writing imply that this book is a blog? Now that conclusion sounds ridiculous because books and blogs, we know in reality, are two different things. But you don't want to say a conclusion is false just because intuitively you feel like it should be false. You need it to be purely a result of what's happening with these premises. So if I say that this book contains writing, where in this diagram could that book be? Could the book be in this circle? Maybe, because this circle lies inside the larger circle, which is the set of all things that contain writing. Could the book also live here? Well, yes, because according to this premise, all we know about this book is that it contains writing. So this is going to be the book that we're referring to. If the book is out here, then it's outside of the set of things that are blogs. So there are things that contain writing aside from blogs, is kind of what we're saying here. This conclusion then would not follow from these premises. Just because all books contain blogs contain writing and this book contains writing does not imply that this book is a blog. And we see that because that X would have to be in this circle in order for that to be true. So this argument is invalid. Okay, because the conclusion does not necessarily follow from those premises. Let's take a look at another example. Some philosophers are absent-minded. Nicole is a philosopher. The conclusion here is Nicole is absent-minded. So let's analyze this. The first premise is going to give us our diagram in this case. Some philosophers are absent-minded. Some is the quantifier here. It's an existential quantifier. Some does not necessarily mean all. It does not necessarily mean none. It means some. So what are the two things that we're discussing that we need circles for in our diagram? Philosophers and people who are absent-minded. That's what we'll call that. Philosophers and people who are absent-minded. So I'm going to make a circle for philosophers. Now, I need another circle for people who are absent-minded. But where should that circle show up in this diagram? If I mimic what I did here and create a circle that's smaller on the inside, then that set of absent-minded people would be completely contained in the set of philosophers, which would imply that all absent-minded people are philosophers. But that's not what this premise says. This premise says that some philosophers are absent-minded. So that means that some of the elements of this set should belong to the set of absent-minded people, but some of the absent-minded people should not belong to this set. So they shouldn't be completely one contained in the other. They should simply intersect. Okay, so I'm going to call this absent-minded people. Okay. Now this makes sense because some of these philosophers, some of the elements of this set are also in the set of absent-minded people. So if I put an X in here, that's going to represent people who are both philosophers and absent-minded. Now what's the conclusion here? Or sorry, what's the second premise? Nicole is a philosopher. So that all that tells me is that Nicole, which is going to be represented similar to how we represented this book by some mark like an X, that means that she needs to belong to this circle of philosophers. And the question is, do those two premises imply that Nicole is also absent-minded? Well, if Nicole is here, then she would be both a philosopher and absent-minded. So in that case, the conclusion would be true. But does she have to belong there? Nothing in the premises implies that she's in this intersection. All we know is that Nicole is in the circle describing philosophers. It's possible that Nicole is here. And here, if Nicole is a philosopher and she's here, but she's outside of this circle, then she's not necessarily absent-minded. So that means that this conclusion does not automatically follow from these two premises. So again, we have an invalid argument. Okay? Now, be careful here, because I'm not necessarily saying that Nicole is not absent-minded. What I'm saying is that we can't be sure of that from just these two premises. Because again, Nicole could be in this intersecting region, but we don't have enough information to say that definitively. And so really what I'm doing is I'm looking for a place to put Nicole that would make this invalid. And if I can't find any such place, then it must be valid. Okay, let's try another one. Some trucks have sound systems. Some trucks have gun racks. Some trucks with sound systems have gun racks. So that's what this argument is saying. Now notice I have existential quantifiers in both premises as well as my conclusion. So how many circles are we going to need in this diagram? Well, we're actually going to need 3, because we're describing some trucks, not just one truck. Notice when we're talking about one thing, like this book, there's only one book being discussed here, or Nicole, one person named Nicole, we don't do circles for single objects. We represented those so far by these X's. You can use other marks as well, but the X is usually what I'm going to use. But if we're talking about things that belong to larger sets, those sets get circles. So when we say some trucks, are we talking about one truck or potentially many trucks? Well, potentially many. Notice it's plural. We're also talking about sound systems, and we're also talking about gun racks. All of those are plural, and that means that they're not going to be represented by a single mark. So that is going to give us 3 circles. Let's start with the circle for trucks. Okay. Now, some trucks have sound systems. From this first premise, it looks similar to the first premise we had in this example. Some philosophers are absent-minded, and we saw that those 2 circles should overlap, but one should not necessarily contain the other, because that would imply a universal quantifier. All of this thing belong to this thing. So I want an intersecting set of circles here. Some trucks have sound systems. Okay. What does the second premise say? Some trucks have gun racks. So we already have a circle for trucks. I don't need to draw a second one. We're going to use the same one. But I want the circle for gun racks to intersect the circle for trucks. Now here's the question. There's two circles here. Should the circle for gun racks, the set of gun racks, intersect the set of sound systems? Well, the answer is no, because what does that imply? That implies our conclusion. Some trucks with sound systems have gun racks. In other words, I can find a truck that has both. But the premises don't imply that. Even though this is probably true, this is very likely to be something that's true, it's not necessarily a consequence from these premises. Because notice here, if I put the circle for gun racks over here, does this diagram describe both premises? Some trucks have sound systems. Sure. The elements in this intersecting region are trucks with sound systems. So some of these trucks have sound systems. They belong in this intersection. Is my second premise satisfied? Yes. Some trucks have gun racks. There's an overlapping region between the set of trucks and the set of gun racks. So some of the trucks in this, or the trucks in this intersecting region have both. That satisfies that premise. Is there anything in these two premises that suggest that all three circles should have a region that they intersect at? There's nothing in here that suggests that these two circles should be intersecting, only that they should intersect the set of trucks. So when I say some trucks with sound systems have gun racks, well, a truck with a sound system would belong here, right? Some trucks with sound systems. If I look at any of the trucks that have sound systems, they live here. Do any of these have gun racks? The way that I drew this diagram means no. Now again, is this possible? Is it possible for a truck with a sound system to have a gun rack? Of course it is. And on an intuitive level, we can say with pretty much certainty, of course, there's plenty of trucks that have both. But that is, again, not following from these premises. It's just following from your common knowledge about what people put in their trucks. So by constructing the Euler diagram this way, which satisfies the premises, we can't find a valid conclusion here. And so again, it's invalid. I know at this point you're probably asking, are we going to have a valid argument? So far they've all been invalid. Well, let's see. Okay. Next one is involving some universal quantifiers again. All chickens have beaks. All birds have beaks. All chickens are birds. So here's our premises. All chickens have beaks. All birds have beaks. These premises, if we assume that they're true, will the conclusion follow from that? So again, we need to determine how many sets we need to write out. I don't see anything being represented in a singular, represented singularly. The nouns in these sentences are plural. Chickens, beaks, birds. I need 3 circles, one for each of those. Okay, so all chickens have beaks, all birds have beaks. How do we represent this with an Euler diagram? Well, the larger circle is going to be the circle for beaks. Now, why is that? Well, because the circle for chickens, if all chickens are to have beaks, then that means the set of chickens needs to belong to this larger set of things that contain beaks. Chickens. Okay? This makes sense because everything that lives in this circle containing chickens is automatically in the circle of things that contain beaks. So yes, all chickens do in fact have beaks according to this Euler diagram that satisfies this first premise. All birds have beaks. Well, that tells me that the set of birds also lives in the set of things that have beaks. But it gives no description, no implication as far as how the set of birds interacts with the set of chickens. Notice if I put my circle for birds right here, then these two circles, according to these premises, don't have to intersect. They might, but I'm not given anything that would imply that they do, so I'm not going to assume that they intersect. So all chickens have beaks, that's satisfied by this circle being inside the larger one. All birds have beaks, that's satisfied by this circle belonging in the larger one of beaks. Both premises are being described here. Now, is it accurate to say that all chickens are birds? Well, if that were the case, then the set of chickens has to belong inside this set of birds. This circle has to live inside this circle. Now, I could have drawn it that way because that would still satisfy these premises. Both the set of chickens and the set of birds would be inside the larger set of things that have beaks. But because I don't have to draw it that way, because I could have drawn it this way, then I see that to suggest that all chickens are birds is not satisfied here because, again, this circle's not necessarily inside this one. This is an invalid argument. Notice I didn't need to put an X anywhere. If you wanted if you want to say that this is false, what I could do is try to show that the negation is true. What's the negation of all chickens are birds? Well, the negation would be there is a chicken that is not a bird. And if I put an X here, this chicken is not a bird because it doesn't belong to both circles. Now, again, I'm going to keep emphasizing this. Just because that argument is invalid does not mean that the conclusion is false. Okay? Is it true that all chickens are birds? Of course it is. Of course it is. By definition, all chickens are birds. But again, what we're talking about here is not whether or not the conclusion is actually true in reality. We're only concerned with the only thing we're concerned with is if the conclusion is a direct consequence of these premises. Okay? That's a really important distinction to make, because if it were just about if the conclusion were true, then we could ignore the premises entirely and just say, well, based on evidence, based on definition, based on whatever, this conclusion is true. But that's not looking at the argument for that conclusion. That's going off on your own and looking for a separate argument to prove that conclusion true. That's not what we're trying to do. We're trying to determine if arguments are valid or invalid, whether these premises imply that conclusion. Okay, here's another one. All people who drive contribute to air pollution. All people who contribute to air pollution make life a little worse. Some people who live in a suburb make life a little worse. So this one has 3 premises. So far, all of the examples we've looked at have had 2 premises, but that's not necessary. We can have actually any number of premises. It just makes our Euler diagrams more complicated typically. But you can only ever have one conclusion in an argument of this type. So let's start by looking at which things are plural and would require circles. All people who drive contribute to air pollution. So we have people who drive and contribute to air pollution. I can call that things that contribute to air pollution. So we have a couple of circles we'll need to draw here. All people who contribute to air pollution make life a little worse. So again, a reference to things or people who contribute to air pollution and things that make life a little bit worse. So now there's a third circle here. Now some people who live in a suburb make life a little worse. Now we have some people who live in a suburb. Okay, so I'm counting 4 circles here. Let's see how we're going to draw this. All people who drive contribute to air pollution. So we have a universal quantifier, similar to how we did in the previous example. We're going to need one circle inside another. Which one is on the outside? Which one is on the inside? Well, to say that all people who drive contribute to air pollution, the second sentence is going to give me the larger one. Okay? So let's see, I can draw it like this. So how do I want to write this? I'm just going to say contribute to air pollution. Okay? All people who drive should be a circle inside of this. I'm just going to say people who drive. Okay? So notice, just looking at the first premise, this Euler diagram describes that just fine. Okay? Next step, the next premise is all people who contribute to air pollution, so again, that's this outer circle, make life a little worse. So that would imply that there's a larger circle containing both of these with all people who make life a little worse. Okay, so let's do that. People who make life a little worse. Okay. So, how do we know that this describes the second premise? All people who contribute to air pollution make life a little worse. All of the people in this second circle here would be people who contribute to air pollution, and all of them should also belong to the larger circle, people who make life worse. That's what the premise here is saying. So we know that we have these in the right order. Finally, some people who live in a suburb make life a little worse. So now we're talking about people who live in a suburb. That's a new circle. But notice it says some people, not necessarily all people. So we don't want the circle for people who live in a suburb to be completely contained in the circle of people who make life a little worse. We could put it here. People who live in a suburb. Okay, now what's the conclusion that we're analyzing? And before I say that, could I have drawn this circle to intersect either of these two circles? Technically, I could have, but did I need to? Well, the only thing we know about people who live in a suburb is that some of them make life a little worse. Nothing in these premises suggests that people who live in a suburb should intersect either of these other two circles, even though intuitively we could say, yeah, there's definitely going to be people who live in a suburb that contribute to air pollution and who drive, obviously. But the premises don't say that. So now that we've created a diagram for these premises, what is the conclusion? Some people who contribute to air pollution live in a suburb. Well, where do the people who contribute to air pollution live? In this circle. And the way that I drew this diagram, none of those people intersect this circle. Again, I could have drawn the circles to intersect, but I didn't have to. By doing it this way, I haven't violated any of my premises. So if some people who contribute to air pollution live in a suburb, then there should be an intersection between these two circles. But there is not. So again, we have an invalid argument. Okay? And again, it might seem a little bizarre because all of our examples have given us invalid arguments. And we're going to, in the next video, we're going to look at some valid examples, maybe one or two valid examples. But the reason so many of these are coming out invalid is because oftentimes arguments that are used in common language between two people, in politics, in social media, you name it, are invalid arguments. Surprisingly few people know how to construct valid arguments in day-to-day life, and that's a subjective comment, by the way. I'm not saying that that's an absolute truth. That's a subjective comment, but this kind of goes to show that how easy it is to construct an argument that seems like it should be true, you know. And again, this argument here, all chickens have beaks, all birds have beaks, all chickens are birds. The conclusion we know is true, but it's not a valid argument for that conclusion. Maybe you can construct a different argument that would be valid and have the same conclusion. Okay? Let me finish this video here, and we'll look at another example or two in the next video.